Oh, welcome back. Yay, another exciting instructional video. Or not, but at least it helps us interpret these equilibrium constants a little bit. Man, when I first started to study these equilibrium constants, it took me quite some time to make heads or tails of it. So if it takes you some time, don't feel bad about that. Here's just a short several page clip with regards to how do the equilibrium constants Kp and Kc connect to each other. This is for concentration, of course. Maybe not, of course. Maybe forgotten. This is for pressure. So if I'm talking about a gas, I can talk about the pressure or the concentration. If I'm talking about something in aqueous equilibrium, then I should probably just talk about the molar concentrations. But you can mix them back and forth if you're talking about gases. But they're not always exactly the same thing. They might be different, or they might be the same. Let's find out more. Here's the connection, the key equation. The equilibrium constant in terms of concentration might be equal to the equilibrium constant with regards to pressure, with respect to pressure. If this is zero, the gas constant is not zero. The Kelvin temperature can't be zero. Well, it could be zero, but that's silly. Everything would be frozen solid if that was the case. The thing is this right here, the change in the number of gas moles from products to reactants. So let me shrink that down a little bit. There we go. So here's the deal. Almost always by convention, the change in some quantity is ending minus beginning. So I go the ending gas moles as described by the stoichiometry of the balanced equation as compared to the beginning number of gas moles. So for example, here's a couple of equilibria. 2 gas moles, 1 gas mole, in equilibrium with 2 more gas moles and 1 more gas mole. So in other words, I just take 2 plus 1, which gives me 3, minus 2 plus 1, which gives me 3. And so here I'm not changing the number of gas moles at all. On the left-hand side I have 1, 2, 3 moles of gas. On the right-hand side I have 1, 2, 3 moles of gas in the equilibrium. And so for this one, the Kp and the Kc would be exactly the same because the delta n was 0. If the delta n is 0, anything to the 0 power is 1, and this one equals that one. Some other examples of how to find delta n. Here's an equilibrium between nitrogen, hydrogen, and ammonia. 2 moles over here, product moles minus reactant moles. 3 moles here, but there's 1 more mole over here. So I wrote 2 minus 4, and that gives me a negative 2, so the exponent here would be a negative 2. This equilibrium has 1 mole of gas here, 1 mole of gas here, and 1 mole of gas here. So, 2 moles of gas as products over here, minus 1 mole of gas. So this one created more moles of gas, in looking left to right, in any case. Delta n equals 1. Or, remember, pure solids and pure liquids aren't even considered or written in the equilibrium constant expression. So here I have 1 mole of gas and 0 moles of gas. 1 mole of gas from 0 moles of gas gives me a change of positive 1. And that would be my delta n in the exponent. Here's a good one. Under particular conditions, this equilibrium has 0.2 moles of CO, 0.73 moles of O2, 2.5 moles of CO2 in a 1 liter container, 100 degrees Celsius. I don't need that initially, but looks like the data I'm given hints to me that I'm going to have to find the concentration constant. So I take the product in the upstairs to the squared power, the reactants in the denominator, this one to the squared power. It's in a 1 liter container, so 2.51 moles of CO2 goes upstairs. I'm sorry, that would be moles per liter. And this would be moles per liter. And this would be moles per liter. I need to fix that. In any case, it's in a 1 liter container. 0.12 molarity, 0.73 molarity. Oh, I forgot to square that one. Dang. Alright, sorry about that. I had to go fix that. I could not live with it. So, let's see. Oh yeah, I had said it was moles, but it's molarity because we're square brackets, molar concentration, Kc, the equilibrium constant with respect to concentrations. And now my number comes out to almost 600. So it seems like this is much bigger than these down here. Or in other words, I can say I'm pretty sure this is in much larger concentrations usually than this down here. This reaction tends to lie to the right, forming lots of products at this particular temperature. Although if you change the temperature, then all bets are off, the constant changes, and we reevaluate everything. So, oh yes, and so what's the delta N for this reaction? Ending number of moles minus the beginning number of moles. There's 3 moles over here, 2 moles over here. So how about 2 minus 3 gives you 1. So 500 was the original equilibrium concentration constant, and my Kelvin temperature, my gas constant, 2 minus 3, oh wait, right, 2 minus 3 is negative 1, so it's basically 599 divided by 30.6, which is that product, and my constant is still larger than 1, descriptive of the pressures that change, or how the pressures relate to each other. There we go. Alright, another example. Let's see. Here I have a solid. Oh, and over here I have another solid, so let's not let those solids get in the way. But my concentration constant, 1.1, I'm told that value at 300 Kelvin. Alright, so if I know Kc, can I find Kp? Well, there's 2 moles of gas over here. That's not even in the constant expression. There's 1 mole of gas here, so that's 3 moles of gas. 3 moles of gaseous products minus 1 mole of gaseous reactant. And that looks like a delta N of 3 minus 1 is 2. My constant was 1.1. My Kelvin temperature of 300. And let's see. Sometimes the constants can change drastically, going from Kc to Kp, attempting to describe how the number of gas moles change. It's reflective of that. Okay, let's try one more example, I think. I believe I have one more. Yep. Carbon monoxide, 2 molecules in equilibrium with an oxygen gas molecule and 2 carbon dioxide molecules. Again, in this problem, I'm told atmospheres. Oh, I'm told some data. So 0.00032, 0.0051 atmospheres, 0.105 atmospheres, and my pressure constant. In the numerator, 0.105, that's this one, to the squared power. In the denominator, carbon monoxide pressure squared, there's a 2 there, square that one, 0.051. And I find it to be very, very large. Ooh, goodness, that's 21 million. These equilibrium constants are, for our purposes, unitless, although technically we might include units, but we're kind of brushing over that for now. And again, if this were at a specific temperature, then I could take that pressure constant and convert it into a concentration constant. Oh yes, should we count those moles again? There's 2 moles of gas over here, 1, 2, 3 moles of gas over here, so 2 minus 3 is again... Oh, I made a mistake there as well. Well, I better fix that. Let's see, how would this change? 2 minus 3 is negative 1, so this should be to the negative 1 power. So, if this is to the negative 1 power over here, it's basically in the denominator, so I'd multiply both sides. So how about 2.11 multiplied times by 0.058? And I will change it on the PDF, and that brings it down to probably 3.64 times 10 to the 5th power, I believe. I'll have to look into that. Anyways, it's still large, but it's not quite this large. Well, that's something to lose some sleep over, but thanks for watching. See you in class. Have a good one.